fetal and placental weight as a function of time. The data is presented in the form of the derivative of W of t because the growth rate was looked at as the change in weight per unit time, also known as Wt over dt. Since W of t represents the fetal and placental weight as a function of time, this is the first derivative of that function. Letting W equal fetal and placental weight, the change in weight per unit time is represented also as dW over WdT. In Figure 1 and Figure 2, the number of births that were originally represented in weeks are now converted to days. Also, the grams for the fetus and the placenta were estimated by using a ruler based off of the graph from the article. In Figure 1, the slope-intercept formula is represented as y equals 0.0544x plus 12.085. The r-squared value is 0.1367, and x equals the number of births per day, and y equals the fetus in grams per day. In Figure 2, the y-intercept formula is represented as y equals 0.00904557x plus 14.3832. The r-squared value is 0.01318. On the x-axis is the placenta in grams per day, and the y-axis is the number of births per day. When comparing the r-squared values for both Figure 1 and 2, they fit within a polynomial degree of 1, and they both did not have a precise regression. Since Figure 1 had an r-squared value of 0.1367 and Figure 2 had an r-squared value of 0.0132, Figure 1 had a better line of fit, but it still wasn't precise. In Figure 1 for the polynomial of the fourth degree, x is still represented as the number of births per day and y is still represented as the grams of the fetus per day. For the y-intercept function, y equals negative 1.5 times 10 to the negative 7th x to the fourth power plus 0.00009232 x to the third power minus 0.01753 x squared plus 1.1395 x plus 4.2329. The r-squared value here is 0.4938. Figure 2 for the polynomial of the fourth degree, x equals the number of births per day and y equals the placenta in grams per day. For the y-intercept function, y equals 2.7066 times 10 to the negative 7th x to the fourth minus 0.0001943 x to the third plus 0.04893 x squared minus 4.9825x plus 181.219. The x squared value here is 0.8099. When comparing Figure 1 and Figure 2 r-squared values with the new polynomial degree of 4, they both have a much better fit compared to the linear polynomial. Since the r-squared value for Figure 1 is 0.4938, and in Figure 2, like I said before, the r-squared value is 0.8099, this time Figure 2 had a much better line of fit, and it was more precise since it was closer to the number 1. Using a polynomial of the fourth degree is better for a more accurate representation of data because there isn't a specific type of symmetry. There are more than 5 data points and multiple points of inflection.
Second derivative graph and function of fetal growth. The graph and function of the second derivative demonstrate the change in the rate of fetal growth over time in days. The x-axis is growth rate and the y-axis is time in days, and Wf of x is as growth rate. The red vertical lines through the first and second derivative graph represent where the possible points of inflection occur. This was also determined through Wolfram alpha, setting the second derivative to 0 and getting the possible points of inflection out. Then, having these possible points of inflection, we need to conduct the second derivative test to determine if there are actual points of inflection. The second derivative test determined inflection points of fetal weight. All 3 points were determined to be inflection points since there was a change in concavity at each point. The second derivative graph and function of placental weight. The graph and function of the second derivative demonstrate the change in the rate of placental growth over time in days. The x-axis represents the growth rate, the y-axis represents the time in days. The second derivative function was determined from the first derivative of the placental growth rate function. The x is defined as the time in days, Wp of x as growth rate. The blue vertical lines going through the first and second derivative graph represent the possible points of inflection which were also determined from Wolfram alpha. G of x is the first derivative and the p of x is the second derivative. The second derivative was set equal to 0 to determine the possible points of inflection. The second derivative test to determine inflection points of placental weight. All 3 points were determined to be inflection points since there was a change in concavity at each point. This is the actual physical/physiological interpretation of these inflection points. So when we are looking at the first derivative graphs of fetal and placental growth rates, it seems that these graphs have peaks and dips. And at these peaks and dips are inflection points, which means that the growth rate is either increasing or decreasing. The placental growth rate seems to be decreasing around 96 days, and then the growth rate starts to increase. On the other hand, the fetal growth rate seems to be increasing around 50 days, and then the growth rate starts to decrease. According to the Forbes article, the placenta weighs more than the fetus early on in the pregnancy and then drops. Next, from 96 up until 189 days, the placental growth rate seems to be increasing. The fetal growth rate seems to be decreasing from 50 up until 146 days. These inflection points mean that the change in placenta growth rate decreases early on in the gestation period but then peaks around mid-pregnancy around 189 days. This is also seen in the graph in the Forbes article, which shows the placenta peak in the growth rate around 175 days. However, the fetal growth rate has two peaks in the first derivative graph. The growth rate peaks at the beginning of around 50 days and then starts to decrease and hits the lowest growth rate mid-pregnancy around 146 days. This is because the calcium content of the placenta increases around mid-pregnancy, leading to fetal nutrition compromisation. Finally, from 189 days up until 253 days, placental growth rate is decreasing. The fetal growth rate is increasing from 146 days up until 249 days. In the Forbes article graph, it is seen that the fetal peak in growth rate is around 252 days. This is confirmed with the 249 days inflection point, the second peak. The fetal growth rate peaks around towards the end of the gestation period because the fetus is getting fully developed, so there is an increase in growth rate until that certain point of 252 days. And then the growth rate starts to decrease because the fetus is fully developed and ready for birth, so no more real growth is required towards the end. Next, the placental growth rate decreases around mid-gestation period, but then the growth rate increases towards the end because the fetus is fully developed and needs a lot more nutrients. So the placenta needs to be growing in order to keep up with the fully developed fetus's needs. The relationship between fetal weight and placental weight inflection points. When the fetal growth rate is increasing, the placental growth rate is decreasing because the fetus is taking up more space. When the placental growth rate is increasing, the fetal growth rate decreases. It can be seen in the first derivative graph where the fetal growth rate peaks. Those are the lowest points on the placental growth rate graph of the first derivative, and vice versa. These inflection points on each graph occur around the same time in days. The fetal growth rate is increasing, the placental growth rate is decreasing because the fetus is taking up more space. When the placental growth rate is increasing, the fetal growth rate decreases. It can be seen in the first derivative graph where the fetal growth rate peaks. Those are the lowest points on the placental growth rate graph of the first derivative, and vice versa. These inflection points on each graph occur around the same time in days, but they represent a different change in concavity because the two have an inverse relationship. The inverse relationship is also seen in the second derivative graph. The fetal growth rate y values lie beneath the x-axis, while the placenta growth rate y values lie above the x-axis. This makes sense because the growth of one depletes the other of nutrients, thus decreasing and or increasing the other's growth rate. The placenta weight in grams as a function of time in days was determined from the fourth degree polynomial. The, the antiderivative was taken of the fourth degree polynomial, and once the antiderivative was taken, it was set equal to 120 grams, and the f value, also known as the constant or c value, was determined as 3.22579 and was plugged back into the WP of x formula, and which was the antiderivative formula. Figure 5 represents the placenta weight in grams as a function of time in days. The blue graph is the graph of the antiderivative. The red graph is the graph of the first derivative. The fetal weight in grams as a function of time in days function was determined from the fourth degree polynomial whose antiderivative was taken in decimals. The antiderivative was then set equal to 100 grams and solved for f. The f value, also known as the c or constant value, was determined to be 4.28183 and was plugged back into the antiderivative formula of wf of x. Figure 6 represents the fetal weight in grams as a function of time in days. The green graph represents the antiderivative function, while the red graph represents the first derivative.
In Figure 7, placental volume is represented in milliliters on the y-axis as a function of the week of gestation on the x-axis. The quadratic polynomial that best defines the function is 0.00113196 x to the fourth power minus 0.107044 x cubed plus 3.32383 x squared minus 23.6765 x, with an r-square valued of 0.9953. The placental volume at time 0 would be 0 milliliters. Reportedly, the placenta is fully formed by 18 to 20 weeks, but continues to grow throughout pregnancy as shown in the previous graph. This makes sense because no time would have spanned in order for the fetus's placenta to begin its actual growth period. This calculation was done by substituting 0 for x in the above-mentioned equation, created by plugging in the a, b, c, and d values provided by Desmos. This yielded a y value of 0. Inflection points refer to a change in concavity of a function, meaning that the sign of the slope of that particular function changes from either decreasing to increasing or increasing to decreasing. Inflection points can be calculated by finding when the second derivative of f of x is 0. For the placental volume data, our values were based off of actual numerical data provided to us, making for a more accurate inflection, whereas the placental weight data from Forbes is based off of an image of a graph, and therefore we relied on our ability to distinguish different concavities in order to determine the inflection points. The data cannot be directly compared because they differ in accuracy based on different means of finding the inflection points. The inflection points of the first graph occur around weeks 15 and 31. The inflection points of the second graph occur around weeks 14, 27, and 36. Overall, the weeks during which the inflection points occurred had some overlap among the two different graphs, but the specific weeks were never exactly the same. The first inflection points for placental volume and placental weight are 14 weeks and 15 weeks respectively, which demonstrates the logical relationship between volume and weight, which tend to be codependent in nature. The second and final point of inflection for placental volume occurs at week 31, which falls between the two final inflection points for placental weight at weeks 27 and 36. Whether or not this data can be trusted is questionable based on the results of the experiment we used for placental volume as a function of time. We are not provided with the conclusions of the experiment which studied the effects of exercise on pregnancy, specifically average volume of the placenta. If the placenta showed that frequency at which the mother exercises has no effect on the volume of her fetus's placenta, then we can trust the data in this experiment. If the study were to show that exercising does have an effect on the placental volume, then the data we used from the experiment could be a misrepresentation of the general public, since many pregnant women do exercise during pregnancy, and the data does not account for any of those women. The source of the placental weight data was obtained from Forbes. In this article, both human and rhesus monkey fetuses are mentioned, and it is unclear which the data represents or if it is an average. According to Human Placenta Project, how does the placenta form? There's a significant change in oxygen supplied to the placenta after 13 weeks of pregnancy, when the placenta develops to bring oxygen and nutrients to the fetus. This is reflected by an inflection point at week 13 on the Forbes placental weight graph, where the slope goes from positive to negative. According to pregnancy and childbirth, as human chorionic gonadotropin levels fall, there's an increased release of human placental lactogen. HPL increases in parallel with the size of the placenta and correlates well with fetal and placental weight. HCG levels seem to drop at around weeks 13 through 15 on average, which also justifies the inflection point at this time. According to Avery's diseases of the newborn, placental maturation at the end of pregnancy is associated with increase in substrate transfer, a slowing of placental growth, and a plateau in fetal growth near term. This is represented by a negative concavity in the Forbes fetal growth graph, but a positive concavity in the Forbes placental growth graph. Typical pregnancies last about 40 weeks, meaning that it is safe to consider 36 weeks the end of the pregnancy. This justifies the inflection points that occur at 36 weeks on both the fetal growth and placental weight graphs.